Hello dear students. So today we are going to start about DC machines. We will solve some numericals. So just let us see first the EMF equation of the DC machines. Uh, then we will solve the numericals. So here we can see a DC machine. Structure diagram of the DC machine. This one is a stator and this one is the rotor. So a stator is excited by DC supply. So you can see the cross and dots here shows the winding and the direction of the current in the winding. So this cross and dots, so winding is wounded in such a way that this produces north pole and this is producing south pole. And suppose the shaft is rotating, when it is generator, the shaft is rotating in this direction. So when it is rotating in this direction, there are slots in the rotor, and they are the armature slots. They are armature conductors. So in the armature conductors, the EMF will be induced, and you can see the cross means current is going inside the conductor. The current is going inside the conductor. So when conductor is rotating in this direction, the current is induced in the conductor bars in the rotors, and you can see this is the cross here. So current is going inside the conductor bars, and this is dot here. So this side of the conductor bar, the current is coming outside, and these are the brushes. This is the brushes which is placed in magnetic neutral axis to tap the current. Okay, so the flux is constant here, and let's say the flux per pole is phi. Flux per pole is phi. Let's phi be the flux per pole of the machine, and it is expressed in Weber. P be the number of poles. P be the number of poles. Okay, here in this scenario, in this machine given, the number of poles is 2. Okay, the number of poles is 2. Z is number of conductors, total number of conductors. Total number of conductors. And n is the speed. Let n is the speed in RPM. N is the speed in RPM, that is revolution per minute. RPM is revolution per minute. N speed can also be given in omega. So omega is in radian per second. So if it is given in omega, we can convert in the radian omega to n by formula. Omega is equal to 2 pi n divided by 60. This is the formula we can use to convert into omega, or to convert in omega or n in respectively. Okay, now we can have and another parameter is A, which is equal to the number of parallel paths. Number of parallel paths. So number of parallel, what does this mean? The number of parallel paths. So winding in the armature, the winding is in such a way. See, there can be many types of windings: simplex, duplex, wave winding, or lap winding. So there are two types of winding: lap winding and wave winding. Okay, so when it is lap winding, the number of parallel paths are 2. Okay, and when we increase the number of parallel paths, suppose in the machine, if we want to increase the rating of the current rating of the machine, so number of parallel paths we want to increase, so then we make a winding in such a way the number of parallel paths are used. So that we use lap winding machine. Lap winding, in lap winding, the number of parallel paths is equal to the number of poles. So we increase the number of poles and we increase the number of parallel paths. So and we make the number of parallel paths equal to the number of poles. So in that type of scenario, the number of in that type of scenario, the current rating of the machine increases. This is same as when we want to increase the current, we can arrange the machine. We can arrange the battery in parallel. If we connect the battery in the parallel, the current increases. If we connect the batteries in the series, the voltage rating of the machine increases. So each conductor is acting like a small battery. Here, each conductor is acting like a small battery. If you want to connect, so all is connected into series or parallel to make the particular rating of the machine. Okay. So A can be of two type. So this is equal to 2 for wave winding, for wave winding, and this is equal to P for lap winding. Okay. So when the conductor, when this is rotating, when this rotor is rotating, armature is on the rotor and rotor is rotating, this conductor cuts this flux phi. You can see the one phi is coming from this circuit, magnetic circuit, another phi is coming from this magnetic circuit. Total equals to phi. So each magnetic circuit providing flux phi by 2. Okay, so conductor is cutting flux. So due to the cutting of the flux of the by cutting the flux, because of the cutting the flux, because of the cutting of the flux by the conductor, EMF is induced in the conductor, and that EMF can be given as, that EMF we can write as, that EMF we can write as EMF generated is equal to EMF generated is equal to EA is equal to phi into Z into N divided by 60 into P by A. P by A. P is the number of poles, A is the parallel paths. Phi means this EMF, generated EMF, depends upon the flux per pole, depends upon the total number of the conductors, depends upon the at what speed the rotor is rotating, depends upon the directly proportional to the number of poles. Okay, so in a particular machine, see, in a particular machine, this Z, P and A can be constant. So I can write this Z divide Z into P over 60A. This is constant for a particular machine. This is constant, and this flux can be changed depending upon the supply in the stator. Depending upon the by varying the supply in the stator, the flux can be changed and the speed of rotation can be changed. So that's why I can write this K into phi into N. So K is a constant. K is the constant. Okay, or K is a constant, or N can also be replaced as omega is equal to 2 pi N upon 60. So N I can replace as 60 into omega divided by 2 pi. So this same expression I can write in terms of omega as Z into T divided by 60A into phi, and in place of N I can write 60 into omega divided by 2 pi. So 60 here cancel out, in terms of omega I can write Z P divided by 2 pi. Then now here is on this one is the value of the constant into pi into omega. So when it is in omega, the constant is this. This is, suppose this is k1, so I can write this is k2 pi into omega. K2 pi into omega. Okay. So let us do some questions. So let's do problem number 1. So here given in the given question it is given as there are 8 pole wave connected armature. So let us write what is given in the question. Number of poles, 8 poles. So P is equal to 8, 8 poles wave connected. It means A is equal to 2. Wave connected armatures has 600 conductors. It means Z is equal to 600. And it is driven at 625 revolution per minute. So this n is 625. N is 625. It's given in 6 revolution per minute. 625 RPM. So unit of n is always in RPM, revolution per minute. In 1 minute, how many revolution the shafts makes? If the flux per pole, and the flux per pole phi is given as flux per pole is 20 milliweber, determine the generated EMF. We have to determine the generated EMF. So the generated EMF we can write as generated EMF we can write as EA. The generated EMF is equal to EA. The generated EMF is equal to Z into P divided by 60 into A into pi into N. Okay, so here we will put here as Z is 600, T is 8 upon 60, A is 2 into pi. Pi is 20 into 10 to the power minus 3, which is equals milliweber, and into n is 625. So let us put these values in calculator. Yeah, so this is our calculator. So this is 600 into 600 into 8 into 20 into 10 to the power minus 3 into 625 and 60 into 2. So this is equal to 500 volt. So we are getting this as 500 volt. This is answer, 500 volt. Let us do next question. In the problem 2, we have 4 pole generator and this is lap wounded. It means the number of parallel paths here is equal to the number of poles with 50 slots, with 16 conductor per slot. So their total number of slots is 50 and each slot there are 16 conductors. So total number of conductors can be 50 into 16. The useful flux per pole is 30 milliweber. Determine the speed at which the machine is to be driven to generate the EMF of 240 volt. Okay, so here we have to determine the speed. So let us see. So first we will write what are the given in the problems. So number of poles is given 4. It's lap wounded machine. So A is equal to 4. Number of poles, if A is equal to the number of poles, which is equal to 4. Z, now find the Z. Z is 50 into 16. 50 into 16. Okay, which is equal to because per slot 16 conductors are there and total number of slots are 50. So 50 into 16 is equal to 800. Total number of conductors is 800. 800 conductors we have. Now useful flux per pole. The flux per pole is 30 milliweber. Okay, and EMF generated is 240 volt. Okay, so we have to find the n is what. So we know the ea can be written as uh, ea can be written as z, number of conductors into poles, divided by 60 into a into 5 into n. Okay, this we can write. So let us write like this. So ea is 240 volt. This is equal to z. Z is 800 into T. T is 4 divided by 60 into P into A. A is also 4 into 30 milliweber. 30 into 10 to the power minus 3 into N. So this we got. So 4 this cancel out. So let us do the calculation of this much quantity. So let us do. This is 800 into 30 into 10 to power minus 3 divided by 60. This is equal to which is equal to 40, which is equal to 0.4. So we can write here, or 240 is equal to 0.4 into n, or n I can write here, n is equal to 240 divided by 0.4, which is equal to 240 divided by that answer is equal to 600 rpm. So we got here is 600 rpm, revolution per minute. This is our answer. So let us do next. So let us do next question. So in the problem number 3, it is given as it is an 8-pole lap wounded armature. 8-pole lap wounded. Number of poles is 8. Lap wounded. Parallel path is equal to number of poles. Armature has 1200 conductors. 1200 conductors, and the flux per pole is also given. Determine the EMF generated when running at 500 revolution per minute. So here also we have to determine the EMF generated. So let us write lap 8-pole machines. So P is equal to 8. Lap wounded, so A is equal to P is equal to 8, and Z is equal to 1200 conductors. Flux is equal to flux per pole is 0.03 Weber, and N is equal to 500 rpm. N is equal to 500 rpm. 500 rpm revolution per minute. So we have to determine the EA. So EA we know, EA is equal to number of conductors into poles divided by 60 into A into 5 into N, which is equal to Z. This is equal to Z is 1200 into 8 divided by 60 into 8 into 0.03 Weber into 500. So 8 this cancel out, this cancel, 0 this cancel out, 6 2 the 12 20. So we have 500 into 20 into 0.03. So we have 500 into 20 into 0.03. This is equal to 300. So we got 300 volt here. This is our answer. Let's proceed to the next question. The next question tells us that determine the generated EMF in the problem 3 if the armature is wave wounded. So if it was wave wounded, the A would have been equal to 2. So let us just proceed here to this. So if it was wave wounded, the EA would have been EA is equal to 1200 into 8 divided by 60 into 2 into 0.03 into 500. So you can see here 2 2 is 4, 4 2 is 2 4 is 8, 0 0 cancel. So we will have 6 2 is 12 20. So we will have 20 into 500. So now 4 will also come into picture. It will be multiplied with 4. So it's, you can see the rating has increased now. So voltage rating has increased. Now the voltage is 1200 volt. Is the rating 1200 volt? 1200 volt. Okay. Let's proceed to the further question. So next question number 5 is so DC wounded generator, a shunt DC wounded generator is given and it is running at a constant speed. Okay, generates a voltage of 150 volt. Okay, so when it is running at a constant speed, generating at a voltage of 150 volt at a certain value of field current. Okay, so determine the change in the generated voltage when the field current is reduced by 20%. Okay, assuming the flux proportional to the field current. Okay, so in this question you can see the same generator is same, so it means the constant, which means I can write if the generator is same, so EA generated, the voltage generator is equal to, I can write K into phi into N, because other parameters, the Z will not be changed, the number of poles will not be changed, the parallel path cannot change. So this EMF is directly proportional, you can write directly proportional to phi and N, directly proportional to the flux and the speed. And here you can see the generator is rotating at a constant speed. It means EA here is directly proportional to 5 only. The N is also constant, the directly proportional to 5 only. Okay, and phi, you can say the phi is also directly proportional to IF, the field current. The flux produced is directly proportional to field current. Okay, so I can write here is EA directly proportional to IF, directly proportional to I. We are assuming that this phi is the flux produced is directly proportional to the field current. If we increase the field current, the flux will increase. Okay, when saturation is not happening. So we are just assuming that the saturation, when the saturation is not happening, so I can write EA is directly proportional to IF. Okay, EA is directly proportional to IF. So I can write because because of using this proportionality, we can write EA1 by EA2 is equal to IF1 upon IF2. So EA1, it means when IF is original, IF is some value IF, EA is producing 150 volt in some certain value of field current. That certain value, let us assume that IF, it is producing 150 volt. So let us write that. So it is producing 150 volt at certain value of IF. Now I have to find what is the voltage produced now when IF is reduced by 20%. IF is reduced by 20% means I can write it is 0.8 IF. IF is reduced by 20%, so I can write this another IF2 as 0.8 IF. So this IF cancel out. Why I'm writing like something is reduced by 20%. 20% is reduced. Something is unit something is X and it is reduced by 20%, decreased by 20%. 20% decreased. So this becomes the is X becomes 0.8 of X. That is 80% of X. I can write that. So similar thing I am using here. So I can write EA2. The next EMF generated, the new EMF generated would be 0.8 times 150, which is equal to 150 into 0.8, which is equal to 120 volt. 120 volt. So this is our answer. Hope it is clear. Yeah, let us do next question. The problem number 6. So in this problem, a DC generator is given and it is running at 30 revolution per second. So N is given here and N is given in revolution per second, and by revolving 30 revolution per second, a generator is generates EMF of 20 EMF of 200 volt. So let us write N1 is equal to 30 revolution per second, and E1, the generated EMF EA1 is equal to 200 volt. Determine the percentage increase in the flux per pole required to generate 250 volt at 20 revolution per second. So EA, so N2 is given. I have to now the speed of the generator is N2, which is 20 revolution per second, and the generated EMF required to generated EMF is EA2, which is equal to 250 volt. I have to find what should be the percentage increase in the flux per pole. Phi I have to find. Phi, let phi 1 be phi. Then I have to find what is the phi 2. How much is the phi 2 percentage? How much is the phi 2 increase in the flux, percentage increase in the flux should be? So here see, same generator is there, so I can write E is directly proportional to phi into N. E is directly proportional to phi into N, or which implies that I can write E1 by E2 is equal to phi 1 N1 by phi 2 N2, which implies that I can write E1 is 200 volt, E2 is 250 required, phi 1 is 5, N1 is 30, phi 2 is, I have to find phi 2, this I have to find, how much is the phi 2, I have to find, and N2 is 20, okay. So this I have to find. So 0 0 cancel, this 0 0 0 cancel, so I can write phi 2 is equal to this will go this side, 5 4 are 20, 5 5 are 25, so this will go this side, okay. So 3 into 5 divided by 2 into 4, 5, okay. So 15 by 8, so 15 by 8 how much? 15 divided by 8 is equal to 1.875, 1.875, or I can write phi 2 is equal to 1.8755. It means, you see how much is the increment. So you can see how much is the increment. So this 0.875. So in percentage I can write this is the phi 2 is increased by phi 2 is increased by 87.5%. 87.5%. Hope this is clear. Let's move to the next example, next questions. Now we have practice questions, so let us do that. So these are our practice questions. So let us attempt the question number 1. This one: a 4-pole wave connected armature of a DC machine has 750 conductors and is driven by 720 revolution per minute. If the usual flux per pole is 15 milliweber, determine the generated EMF. So here we will write as usual, T is equal to 4 and number of conductors Z is equal to 750 and N is equal to 720 RPM. Speed is equal to N is equal to 720 RPM and yeah. So and flux per pole, useful flux per pole is given as 15 milliweber. So we have to find the generated EMF. So E I can write EA as generated EMF as P into Z divided by 60 Z into P divided by 60 A into 5 into N. So if you put the values, Z is equal to 750, Z is equal to 750, number of poles 4 divided by 60 and this generator is wave bounded. This generator is wave bounded, so A is equal to 2 into 2 and pi is 15 into 10 power minus 3 and N is equal to 720. 720. So 2 2s are 4, 0 0 cancel out, 6 12 times 12 120. So we have left is 75 into 2, 75 into 2 into 15 into 10 to the power minus 3 into 120 is equal to 270 volt. Equal to 270 volt. Let's see this one. Question number 2. 6 pole B is equal to 6. Lap winded means A is equal to P is equal to 6 with 40 slots with 20 conductors per slot. So Z is equal to number of conductors is equal to 40 into 20, which is equal to 800 conductors. The flux per pole phi is equal to 25 into 10 power minus 3 Weber, 25 milliweber. Speed, we have to calculate speed N. We have to calculate N. If the generated EMF is given, generated EMF EA is given as 300 volt. EA is 300 volt. Then what is N? What is the speed? So we can write EA is equal to, EA is equal to, same formula we will use, Z into P divided by 60 into A, pi into N. Okay. Putting the values, we get EA 300 is equal to Z into P 800 into P is 6 divided by 60 into 6 into 5 is 25 into 10 to the power minus 3, and then n we have to find. And 6 cancel, 0 cancel, we will, and so this 300, this 2 3 are 6, then 40. So we have this 3 will be multiplied to 300, this 900 is equal to 40 into 25, 40 into 25, 40 into 25 into 10 to the power minus 3, 10 to the power minus 3, which is equal to 1. So this is this whole multiplying this whole is equal to 1. This plus 3 I have sent to this side, so this is 900, so this is 1 into n, so n is equal to 900 rpm. Next, see question number 3, third one. P is given for DC machine as 1000 conductor, Z is equal to 1000, okay, and flux per pole pi is equal to 20 milli Weber, so 20 to 10 to the power minus 3. Determine the EMF generated when running at 600. So if n is equal to 600 rpm, and we have to find the then we have to find the EMF generated for wave wound and lap wound. Means for first one is for A is equal to wave wound, A is equal to 2. So for A is equal to 2, we put EA is equal to ZP divided by 68 into 5 into n, which is equal to Z is 1000, Z is 1000, P number of pole is 4, 60 into A number parallel path 2 for wave winding into 5 is 20 milliweber, 20 into 10 to the power minus 3, and RPM, how much RPM it is moving, is 600 RPM, 600. So this 0 cancel out, 6 10 60, 2 2 4, so how much we will get, 2 2 4. So this 10 to the power minus 3 and 1000 cancel out, it is 400 volt, so this is 400 volt. Now for lap winded A, for lap winding A is equal to P is equal to 4, so 4, so here will be 4, so EA here will be 1000 into 4 divided by 60 into 4 into 20 into 10 to the power minus 3 into 600. So 4 with this cancel out, 0 this cancel out, 6 10. So we have, and this cancel out, we have 200 we have 200 volt. You can see here for lap wounded, the EMF generator has reduced, and similarly we'll see the current, similarly it gets increased. Now see the question number 4, this one. Yeah, revolution. The n is given as 25 revolution per second generates EMF. Yeah, similar I think as we have discussed, similar type of question is there. Yeah, so E is generated EMF is 150. Determine the percentage increase the flux per pole required to generate 100. So this is E1, EA2 is given as 180. So this is N1 and N2 is given as 20 revolution per second. 20 revolution per second. So we know that for particular machine, E is directly proportional to phi into N. So you can write E1 by E2 is equal to phi 1 into N1 divided by phi 2 into N2. Okay. So E1 is given here as E1 is 150, E2 is 180, and phi 1 is let phi, N1 is 20, and phi 2 is phi 2 we have to find, and N2 is N1 is 25 and N2 is 20. N1 is 25, N1 is 25 and N2 is 20. Okay, so 0 0 this cancel out, so this phi 2, so here we will take phi 2, I can write here as 5 5 is 25, 5 4 is 20. So phi 2 here as 5 by 4 into 5 into 18 divided by 15. So 5 3 is 15, 2 2 is 4, 2 9 is 18, 3 3 is 9. So here you can see it is coming to be 3 by 2. 3 by 2 means 1.552, 1.55. You can see the phi 2 has increased 50%. This is 50%. So increase is 50%. Increase in phi 2. Phi 2 is 50%. So we have solved all the questions here. So moving to the next concept of types of DC machines. Types of DC machines. So now we have classification of DC generators. Of DC generators. So there can be a separately excited DC generators, separately excited. There can be shunt excited, and there can be combination of both. There can be series excited, and there can be combination of both shunt and series, that is compound excited. So separately excited, what is the difference is that how they are classified. It is the classification is based on the connection of the field windings. So let us model this generator. So this is the armature. Armature is on the rotor. Armature is basically a coil, okay, which is producing coil, and so it will have some resistance also. So that's armature resistance, and there is a field winding which is producing the flux. So if the field winding is excited to another separate source, then it is called separately excited. So that is VF. So this VF, this field winding is connected to some separate DC source, which is circulating current IF, and this coil may have RF resistance, RF. So this IF can be written as IF here is VF upon RF, and this generator, when rotated, this is when this generator is rotated in this flux, will produce an EMF. We call this that generated EMF, which we have just find out how to calculate this EMF, that is EA, and it has resistance RA, and this when connected to the supply, this is the voltage, this is the terminal voltage, this is terminal voltage is V, and when it is connected to some load, when it is connected to some load, the voltage across the load is V, and the current is going from the armature, this current is I. So in this KVL, by applying this KVL equation, I can write here, by applying this KVL equation, I can write here as V is equal to EA minus IA RA. Okay, so this is the generator equation. V is equal to EA minus IA RA. In shunt excited, what happens? The armature is there. Armature is producing EMF, generating EMF EA. This is armature resistance RA. The field winding is connected in parallel with the armature. Field winding is connected in parallel with the armature, and this has resistance suppose RF, and this is the terminal voltage, this is V, and if load is connected, can have this current, this is the current IA, which is generated by the armature, coming from the armature. This current IA gets divided into two parts, this is IF, and this is load current I, total current you can say I, sorry, this is I current. So IA here is IF plus I. Okay, and IF, what is IF here? IF I can write here as this, the voltage across this is V, the voltage across this, voltage across the field winding is V, so V divided by RF. This is the IF. Okay, and similarly the V I can write here as V is equal to EA minus IA into RA. This voltage I can write here as. So this is the equation for the shunt excited. For series excited, the windings are in the series. So there will be armature resistance and there will be field winding in the series. So this will have RF, and this is the produced generated EMF EA, and this is the terminal voltage. So load is connected across the terminal. So the IA will flow here in this direction. This is RA, this is RF, and this is the voltage you are getting across the terminal V. Okay, so here you can write this equation as V is equal to EA minus IA RA plus RA. Okay, and here you can see the current in the armature current is flowing through the field winding. So IF is equal to here, IF is equal to IA. Here for the series, the IF is equal to IA. Okay, and for compoundly excited machines, there are some windings are in the series with the armature, and some windings are parallel to the armature. So this is armature resistance, this is armature EMF generated. Some windings are in the series with the armature and some windings are in the shunt. this is RA. Okay, so this is the B. Some winding RF1, RF2. Okay, this is. So let us see some questions here now. So we have question here. So the question asks, determine the terminal voltage of a generator which develops an EMF of 200 volt. So the given the questions in the given questions. So the data given is EA. The generated EMF is 200 volt, and the armature current is flowing is IA is 30 amp when it is connected to the load, and it is told that to assume the armature resistance RA as 0.3 ohm. You have to find the terminal voltage. You have to calculate the V. What is V? The terminal voltage. Okay, so V I can write V is equal to EA minus IA into RA. So which can be 200 minus IA 30 into 0.3. This is equal to 30 into 0.3. This is 9. So this is 200 minus 9 is equal to 191 volt. Okay, so simple questions, so simple that solution. Okay, see the next question. So a generator is connected to a 60 ohm load. So let us draw the model. This is the generated EMF. This is the armature resistance. It is connected to a 60 ohm load, 60 ohm load, and current of 8 ampere flows. If the armature resistance is 1 ohm, this is 1 ohm, determine the terminal voltage and generated EMF. Okay, and the current flowing in this here is 8 ampere. So since 8 ampere current is flowing, so 60 into 8, the voltage across this will be, let's V the terminal voltage. The voltage across the load will be 60 into V according to Ohm's law. So V I can write V is equal to 60 into 8, 60 into 8 ampere. So which is equal to 60 into 8, 480 volt, 480 volt. And EA we do not know, E have to find. So we can write V is equal to EA minus IA into RA, or I can write EA is equal to V plus IA into RA, which is equal to 480 plus 8 into 1, which is equal to 488 volt. So simple answer, so simple solution. Now, so this is way we are solving the problem. So let us say proceed to the next problem. Now let us see this problem number 9. So in the given problem, so a separately excited generator develops no load EMF. No load EMF means generated EMF. This is EA 150. So just by reading question, first we write the data, all the data. 150 volt at armature speed of 20 revolution per second. So N is given here as, in the revolution per second, 20 revolution per second, and the flux per pole is given as phi is equal to 0.1 Weber. Okay, determine the generated EMF when the speed increases to 25 revolution per 25 revolution per second. So here this is N1, and it is given that N2 is equal to 25 revolution per second. Then we have to find what is the next generated EMF, EA2. So here it is EA1 is given, EA2 I need to find. Condition is that since it is separately excited, so phi will not change. Phi will only depend upon the field current. So field current is not changing, so phi is constant. So since phi is constant, so I can write E is directly proportional to phi into N. So phi is also constant, so it is directly proportional to now N. So I can write E1 upon E2 is equal to N1 upon N2, or I can write E1 is 150, E2 I need to find, E2, and N1 is 20 and N2 is 25. So easy. uh, 4 for the 24, 5 the 25. So E2 I can write here as, or E2 I can be written here as, E2 is equal to 5 into 150 into 5 divided by 4. Okay, so 1, so you can write here as 150 into 5 divided by 4. So this is 187.5 volt. So E2 I get as 187.5 volt. So this we got. Okay, this was the part A solution. This was the part A. So generated EMF, determine the generated EMF when the speed increases to 25 revolution per second and the flux will remain unchanged. Next, part B. Part B, the speed remains at 20 revolution per second. So here speed in the part B, speed is constant here, and the flux pole per pole is decreased. So here now the speed is constant, N is constant here now. Phi is changing, so I can write E is directly proportional to now phi. E is directly proportional to now phi. Okay, and flux is decreased. So phi 1 was 0.1 Weber, and now flux is decreased to, so phi 1 was 0.1 Weber, and now it is decreased to 0.08 Weber. Phi 2 is 0.08 Weber. So simple, what would be the EMF generated? EA1 we know 150. So you can write simply, I can write E1 by E2 is equal to phi 1 by phi 2, or which we can write 150 upon E2 is equal to phi 1. Phi 1 I can write as 0.1 Weber divided by 0.08 Weber. Okay, okay. So similarly from here I can write E2 is equal to 150 into 0.08 divided by 0.1. So this I can get here as 150 into 0.08 divided by 0.1 is equal to 120. So get here as 120 volt. This is the solution. Okay, now the part C, the speed increases. Now speed is also increasing to 24 revolution per second, and the flux per pole, and the flux is decreased to 0.07. So now both is changing here in the part C. Here in the part C, both is changing. Phi is also changing, and so phi 2 here is changed to 0.07 Weber, and N2 here is changed to 24 revolution per second. So here both is changing, so I can write E generated EMF is directly equal to phi into N. So I can write E1 by E2 is equal to phi 1 by phi 2 into N1 by N2, and we'll put all the data. So E1 is 150, E1 is 150 divided by E2 is equal to phi 1. phi 1 was 0.1, 0.1, and phi 2 is now 0.07, 0.07. N1 was earlier 20, N1 was earlier 20. N1 was earlier 20. Now it has changed to 24. So you can write here as it has changed to 24. 20 and it has changed to 24. So E2, I need to find E2. So I can write here as this. This I can solve in the calculator. Let's simplify this. 0.1 into 20 divided by 0.07 into 24, which we get 25 by 21. So let me write 150 divided by E2 is equal to 25 by 21. Now I will cross multiply and I can write E2 as E2 is equal to 150 into 21 divided by 25. Okay, so this I will get as 150 into 21 divided by 25, which we get 126, because 126 volt. So hope all these answer these two solutions complete. So now we'll see the next questions in the next video. Thank you.